you know, those who are missing the beginning will just be missing sort of the fluffy motivation and lather. So, however, first I'd like to mention that a lot of this work is done in collaboration with John Barrett, who's at DAMTP in Cambridge, and I believe also Perimeter. Matt Leifer, who's at the CQC, Center for Quantum Computation in Waterloo, University of Waterloo. And Alex Wills, who's at the University of Susquehanna. And then the work I'm going to talk about on bit commitment, if I talk about it, is me, Matt Leifer, Ben Toner, who's at CWI Amsterdam, and Oscar Dalston from ETH Zurich. And I guess I'm from the Information Sciences Group, CCS3 at Los Alamos. Okay, so our general research program is to study information processing, what we call general probabilistic theories or convex operational theories. And so why would one want to do this? Well, I mean, the excuse that you use when you're writing grants for quantum computing projects is that you want to, well, what are we doing? We're characterizing quantum and classical theories within a broad framework of theories that somebody, probably Robert Speckman's like to call them foil theories, right? They're neither quantum nor classical, and they allow you to make contrast with what's common to quantum and classical information processing, and maybe understand both better. And so the idea is maybe to look for axiomatizations of, let's say, quantum information, quantum theory, in terms of information processing rather than more mathematical properties. What's going on here? Okay, so this could help you develop protocols if you understand conceptually what are the real conceptual ingredients that go into the power of quantum information processing, whether it's for crypto or computing. It can help you understand the limits to quantum information processing. Maybe it's easier to derive limitations in some broader framework on some huge class of theories that includes quantum and classical. So you might look into, for example, if you come up with a good notion of an oracle, this is something I've been thinking about, can you get Grover-like bounds on some larger class of theories and understand really fundamentally why we can't use a brute force structuralist approach to doing NP-hard problems in polynomial time. And perhaps these structures are useful for modeling information processing in other complex or concurrent systems. And then there's the hubris side of things, which is represented, of course, by, among other people, Chris Fuchs. Maybe information is the essence of quantum physics. And so we might get an analog of Einstein's principle-based accounts of special and general relativity, where the principles have to do with the way information flows in the theory, whether it can be copied and so forth. Right, so I'm not sure what I think about that program of getting the big reconstruction, but it's going to be a lot of fun even if we don't. We're going to learn a lot about the nature of information processing, both in general and in quantum mechanics. Okay, I should mention other people who've worked on characterizing quantum mechanics. Lucian has a nice axiomatic derivation of quantum mechanics, or at least getting you very close to it. Mauro Dariano is working on this recently. There's a nice paper in Commath Phys by Araki in 1980. And there's some more on the formal side, quantum logical characterizations. So we're going to look at a framework that is precisely what Lucian, well, I should say a few things. So it's closely related to a framework that Lucian developed a few years back. It's been used by John Barrett and various people. And then in sort of somewhat different formal representations, it dates back a long time. So I'll call it the convex operational formalism. Basically, you've got a bunch of systems, call them A, B, and C and stuff, and each system has a convex set, omega A, omega B, and so forth, of states. And the role of the states is basically they determine the probabilities of any measurement you could make on the system. And so you have some set of measurement outcomes. You have a convex set of allowable dynamics that take states to states. And then you have something like a tensor, which is a way of either making composite systems by, writing down some theory where you can just cook things up by freely going this tensor that, and then these two things tensor this other thing. Or you might want to have use this same notion of compositeness to recognize composite structure inside some big thing that you already have there, right? So for instance, if you take two Hilbert spaces and you tensor them up, that bipartite structure that you just made is not the only bipartite structure you now have around. There's a whole continuum of ways of viewing, two qubits as a tensor product of two qubits, besides the one you started with. There's one where the Bell basis looks like product states, sort of a virtual, non-local subsystem. So we want to be able to also look into composite systems and get compositeness out. Okay, I'll just quickly go over the main results in case I don't get time to go over them in detail, which I almost certainly won't. So a set of states is clonable. So there's characterization clonability, let's say. A set of states is clonable if and only if the states are perfectly distinguishable by a single measurement, right? So I can make one measurement and know exactly which state from this set I've got just from the answer to that measurement. Set of states is broadcastable. So maybe I'll tell you what cloning is. We want a state, let's call it just rho, although it doesn't need to be quantum, so let's call it omega. Okay, it has to have independent copies, that's cloning. Okay, with broadcasting, we just say, well, I want the marginals to be equal. I want some map, omega from A to A tensor A, 2 copies of A, such that omega goes to some big state, T of omega, T is your map, and you want to look at the reduced state, which we'll define later, on A, and the reduced state on B, and they should both be equal to the original state. This allows correlated copies, right? Okay, well, a set of states is broadcastable, basically if and only if it's in the convex pole of a set of clonable states. And this holds in a lot of generality. The only information you can obtain without disturbance is intrinsically classical information. Sort of like in quantum mechanics, is the information about which superselection sector a state is in. So if you want to make sure that you don't disturb any states in the system, you had better only find out which sector you're in where your theory doesn't allow superposition between the sectors. And so this should be, this broadcastable sets of states. They have the structure of a simplex in our convex framework.
A regular simplex, right?
Excuse me?
Regular simplex? Or just a simplex?
Finite dimensional, if that's relevant to your statement about regular
simplex. But I mean generalization of triangles.
Yeah.
Right?
Probability simplex.
Yeah, okay. Right.
So that's kind of a classical structure. And I think an interesting thing to study is the fact that this classical structure exists in a category. You can formulate this stuff in terms of categories, and it looks like the category has somewhat weaker properties than the ones that are being used in the categorical introductions of classical structure by this Frobenius dagger Frobenius algebra, or whatever. And so it would be nice to abstract this stuff and see what that weaker structure might be. So we've been having some discussions about that. So the point I want to make is that this kind of classical structure is sort of facultative classical information, right? If all your states are in this set, you can just look at, you can look at the vertices of this simplex as if they are classical states, and everything that's going on inside this thing is classical. But superpositions are possible, right? It's just that if you don't work with them, things look classical. The classical structure that's in this information disturbance theorem is intrinsically classical. You never have superpositions in your theory. Yeah, Peter.
So when you say convex hull, you mean you're talking about mixed states, right? Are you?
Yeah. So.
Okay. So a set of pure states would be clonable if and only if it's broadcastable.
Correct. The two notions coincide in the case of pure states, and the question. So in 1996, a bunch of us proved a quantum no broadcasting theorem because we were interested in no cloning as sort of a fundamental property that characterizes quantumness as opposed to classicality, and asking, well, how does this generalize to density matrices? If you just generalize to say, oh, the density matrix rho goes to rho tensor rho, well, forget about quantum. Even classical distributions are not clonable in that sense. So we wanted a notion that would generalize to mixed states and still distinguish quantum from classical. And if you do it in the quantum case, it's sets of commuting density operators that clone. And of course, those lie in a simplex whose vertices are just the projectors onto some orthonormal basis. So it all is consistent with this more general plane. Okay. Exponentially secure bit commitment is possible in any non-classical theory that doesn't have entanglement. I'll probably explain that a bit more later. we've got necessary conditions for conclusive teleportation, and they're actually necessary and sufficient if you require a sort of niceness property that's very close to monoidalness when you have three systems. So I'll explain that in more detail. And that's all pretty simple, and it's closely related to these E and I, or eta and epsilon, whatever you call them, these bell-like objects. Sufficient conditions that are pretty nice for actually deterministic teleportation. So being able to get the measurement outcome, send it to Bob, and have the teleportation always work with probability 1. And finally, I might talk about conditions for ensemble steering. So that's when you have an entangled state, and by making a measure, well, you have a state. Let's just say you have a state. By the choice of measurement on one side of the state, you can make any ensemble, any convex decomposition of the marginal state on the other system. So you can do that in quantum mechanics. And there's a fairly simple, at least sufficient conditions for doing that in these theories. Okay, let me say a little bit more about these convex state spaces. It's a pretty simple concept. You just have some convex set, omega, of states, and you kind of, omega has affine dimension, let's say d minus 1, okay? So that means you can stick the whole thing into a d minus dimensional copy of Rn. But then let's copy this, let's sort of translate this d minus 1 dimensional copy of Rn and stick it into R, and, sorry, so affine dimension is R d minus 1, and we're going to stick it in Rd. And we're just going to make sure it avoids the origin, and then we're going to take the cone that's generated by taking the origin and every ray through every point in this set. And so the point is, these are the normalized states. This is like an unnormalized state space, just like in quantum mechanics. You're talking about unnormalized density operators. It's mathematically useful to have that around, particularly if you want to go towards the category version of this. Okay, by the way, please ask questions if anything's not clear. Right, so now we've got this cone, which I guess I'm going to call A plus. I guess A is sub plus. And so let's just say this vector space A is, let's call RD A. We're, A and B are nice names for systems, so let's start using them. All right, so this is a positive cone. We're going to make a few assumptions about the types of cones we allow as state spaces, but let me make one other observation. Since this is a slice of this cone by an affine hyperplane, so there's a little pointed little edge of the cone that goes behind what you're seeing. Since this omega is a slice of the cone by an affine hyperplane, there's some linear functional that's equal to 1 exactly on that hyperplane. So we'll call this U, or U sub A. And the point is, so when I write set in here, that just means for every little omega that lies in omega, UA of omega is 1. So that's like the trace in quantum mechanics. It picks out the normalized density matrices. Here, it's a linear functional, which in category theoretic terms probably is also a trace, once you get this formulated that way. Its function is just to slice through and pick out the normalized states. So we can say A plus and UA, or just the A and UA, is what Alex likes to call an abstract state space. Now, just a couple of notes on mathematical terminology, or actually assumptions. So you can do this with any cone just by introducing a functional that is strictly positive on the cone. Strictly is important. That will slice the cone and give you some set omega. Now, we want the set omega to be compact and convex, of course. Now, if we start with the convex set here, there's no problem with getting it to be, getting the cone to be convex. But, right, so we actually want omega to be closed. Or another way of doing this is just to say, let's just put conditions on the unnormalized state space. So these cones have to be pointed. What does that mean? Well, we got to the origin here. Now you could Yeah, so what is a cone, right? It's closed under, okay, non-negative scalar multiplication. So a cone, K subset of Rn, let's say. It's closed under non-negative scalar multiplication. Addition, that makes it convex. Some people, like to talk about convex cone. And we also want to say it's pointed. So it contains no subspace. Right? If you just have convex, if you just have these two, you can imagine like a wedge, right? Like you just take some 2D cone, put it in R3, and you just sort of translate it out along, the third axis, and you have this entire third axis, the entire subspace that's still within the cone. Okay, that's bad if you want to chop things type plane and get a compact convex set, because you won't necessarily. In fact, you necessarily won't. Right. So we want pointedness. Okay, and we'll just call this thing. Let's throw in what else we want. Okay, I'll draw a line here. We want something topologically closed. Again, that's so this thing is compact. And then maybe all. No, we want one more thing. We want it to be generating. And I mean, this is just sort of technical, but omega, or the cone, is equivalent, should generate the full Rn as a vector space. If you take it as a set, you should take all linear combinations, so that includes negative and positive combinations, to generate the vector space. Because otherwise, if it weren't generating, well, maybe it's easier to just work in the space that it does generate within that thing. Yeah, Peter.
A few years ago, I tried to do semantics for some programming language based on abstract cones as opposed to concrete ones of positive operators, and I found that there's no way to define the tensor product of two cones. Do you know how to tensor?
Well, I'll talk about that.
Okay.
Good. And yeah, I mean, there's no determined way. There are sort of two ways that are kind of canonical and they're extremal. And we basically take as a tensor product anything that's in between those things. And then, that may or may not satisfy whatever you wanted it to satisfy. All right, so that's the state space. I just wanted to say, this is the same thing as saying that we impose on our vector space A an ordering. So just a partial order, and we say, well, the partial order's got to be compatible with this cone structure, so you can add the inequalities, you can multiply the inequalities by positive scalars. And pointed is actually needed to make it not be a pre-order, but actually an order. And then generating gives it nice properties, and closed makes the order closed. But these three things are equivalent to an ordered linear space. So I'll talk about ordered linear spaces. It's just going to mean that the thing has a distinguished cone. And implicit, in fact, in my use of the term, will be the cone that's generating code. So the abstract state space is basically an ordered linear space with a chosen trace, a chosen linear functional that lies in the interior of the dual cone. What's the dual cone? It's just the cone of all functionals that are positive on everything in the primal cone. So each functional in the dual has to be greater than equal to 0 when evaluated on any point in the primal cone. That's the dual cone. And the dual cone is a natural place for measurement outcomes to lie, right? Because we would like measurement outcomes to be linear functionals from states to the reals, which is the underlying field here.
Can I ask a question?
Yeah.
So you suggested that we should think of omega as being say, r to the minus 1. But what is the real formal condition? Can I take omega to be a 3-element set?
No, omega should be a compact convex set. If you're going to start with omega, you can generate this cone structure, but omega has to be a compact convex set. Whose affine dimension is t minus 1. And then you embed it in RD in this way.
So it's an affine space itself already.
Yeah. All right, so let's get to measurements. So a sort of operational principle that motivates convex structure is the idea that, you know, we're thinking of things operationally. So we've got processes that a system can undergo, and we always assume that if it can undergo one process or another, it can undergo the convex combination of those two, any convex combination of those two processes. So this is sort of a formalism for systems, you know, maybe, for instance, systems that we stand outside of, and we've got classical control, and we've got dice or other events we can condition on that have whatever probabilities we want. And so we use our classical control structure to you know, make convex combinations of any processes we control. Or alternatively, if we're describing processes that aren't under our control, we just want to imagine that there's always a convex combination. So in category theoretic terms, I think you might want to formulate this and say that we're talking about a category that's enriched over the category of ordered linear spaces. In other words, the space of processes from one object to another is always itself a cone. Right? That's what enriched over blah means, is that the Hom sets, the set of processes going from one object, morphisms going from one object to another, are a block. Right? So, all right. So this dual cone has these linear functionals, and you know, we want linear functionals precisely because we want this property that if I do this, I flip a coin, I do this, and I do that, and then I do some measurement, the probability of the measurement outcome is the same, you know, is the same coin flipping probability, so it's a biased coin, as if, yeah, you just take those probabilities and you mix a particular outcome with those probabilities, and that should be the probability of getting the outcome. So, you know, we want measurement outcomes to be linear functionals because they're supposed to commute with mixed preparations. Okay. And you know, same argument goes for dynamics. If I'm picking dynamics for something, I could, you know, those are going to be linear precisely because we want them to commute with mixing a choice of dynamics. Okay. So, formal representation of a measurement is a set of it's an index set, f sub I, and you can get fancier and have continuous sets, but we won't right now, such that some I, f sub I of omega, is equal to the unit. And this has to, sorry, there should be no omega there. So it's a bunch of things that add up to the unit, right? So in quantum mechanics, it's a bunch of POVM elements. They're positive operators, aren't necessarily normalized, and they add up to the identity operator, which is, of course, the unit in quantum mechanics, because the trace of the identity times x is the trace. So these things have to lie in A plus star, which is the dual cone, and they add up to the unit in A. And this is just trivially equivalent to saying the probabilities have to lie between 0 and 1. And for every state, the probabilities of the measurement outcomes must add up to 1, because U is going to evaluate to 1 in the state. Okay, so is this pretty clear to people? Okay. Now, we typically, when we talk about these theories, we take you know, we say the set of, so these are called effects, right? Measurement outcomes are often called effects for historical reasons. We can talk about the philosophy of why they're called that. So one thing we could assume is that the set of effects that a theory actually allows is equal to the full unit interval in the dual cone, A star plus. So any measurement that satisfies these laws, which are basically compatibility with probabilistic interpretation of these things as measurement outcomes, just obeying the rules of probability on each measurement, any such measurement we're going to allow, right? So if we make that assumption, which you don't have to make, it seems very natural. If we make it, then the set of allowed effects are just the full unit interval in the dual cone, right? And remember I said the ordering, right? X is greater than or equal to y, I should just tell you what it is. It's you know, x minus y is in a star plus, or a plus. I mean, whatever cone you're talking about. Here we're talking about a star plus. This is the translation between distinguished cone and order relation, and it's basically an equivalence. And so we're just saying 0 is less than or equal to these things. They're positive, they give us positive probabilities, and they're less than or equal to 1, so they won't ever give us probabilities bigger than 1. Sounds reasonable. You can also cut down the dual cone and say, I want to consider a theory in which, so in a funny way, this assumption is like saying my theory has a convexified version of Gleason's theorem, right? Every measurement that is possible is permitted, and you know, if I just take a set of FIs that add up to the unit, that's sort of my generalization of the notion of an orthonormal basis in Gleason's theorem. I require these things add up to 1, then this is what the measurement outcomes always have this form. So it's kind of a, you know, everything that's possible, every measurement that's sort of logically possible has been thrown into your theory. But we can cut down the dual cone and we can say, no, our operational measurements, you know, lie in some cone A sharp plus, which is a subcone of A star plus. And now we're going to look at 0 UA sharp plus. No, 0 UA, it's just the same old UA. But we require it to be, I don't think we need this, you know, to belong to this A sharp plus. And this is actually a nice thing to be able to do. And if you set this thing up categorically, it turns out it's pretty much just as natural as this.
So,
yeah.
I will ask. So, is the dual is that those operations star and plus they commute?
Star and plus.
The cone you take in the dual space, is that the same thing as the?
Those aren't operations. Star is like an operation. Plus is pretty much just like a name. I mean, it's just, plus is just there to distinguish the vector, ambient vector space A from, it's saying I'm taking this subset that's the positive cone. So there's only one operation here. I don't know if that makes sense.
Is the positive cone in the dual space the same thing as the dual, as all the affine maps out of the positive cone? It's a question.
Yeah.
It is.
I think so.
It should be.
Yeah. I mean, so, you know, at one point Alex formalized everything that way and it confused the heck out of people and we dropped it. It might be useful in an infinite dimensional case where, you know, certain things aren't the same that are the same here.
And so, what are you saying when you say, what is the statement that this interval is a plane by, you know, transferring the order on A to an order on the linear forms?
Yeah.
And this is defined here.
Sorry. This is so.
And no, sorry.
Let me get rid of the star. This just defines the correspondence between a distinguished cone and an order.
All right, but then you're using it to define the
I'm
interval
applying
in
it
the
to
dual
A star
space.
plus here.
So what's
But A star plus has a distinguished cone, and so I'll just write the definition. I said it verbally. But it's the set of all, you know, F in A star, just viewed as unordered, the dual space, linear functional, such that for all omega in A plus, F of omega is greater than or equal to 0. So,
right?
So it's all linear functionals that are positive on states.
So, all right, but that you're constructing the cone given the one in the starting space.
Yeah.
But is there a way to construct it directly with an order structure on the dual space? And
Well, I mean, the point is that once you have this, you induce an order structure on the dual space.
No, I understand
you can
that.
say the order structure on the dual space, and then I'm translating it to this greater equal. You just define greater equal as saying, yeah, this is pointwise ordering of the functionals, right? If the functional is bigger on every point, then it's a bigger functional. So if whatever state I stick in, you know, f of omega is, whatever state omega I stick in, f of omega is greater than or equal to g of omega, then f is greater than or equal to g.
And what
And you have to restrict that, of course, to the states in the positive cone of your primal thing. But it's just another way of doing this.
Okay, is it at least idempotent? So like if I take again the
A
dual
star
at
star
first
equals star. Yes, equals
no,
A
no,
plus.
no, A, it's not A star star I'm looking for. It's
A plus star
plus star plus. Can you?
So let's even be more pedantic. A plus star equals A plus. It's an easy exercise.
Well, star is defined in this way.
Yeah.
But isn't the double star is a vector space? And
We're in finite dimensions here, so.
He defines the star of a cone to be another cone called the dual cone.
Yeah.
So the cone is not growing when you do it. You go to dual space.
It's not. It will grow if you use A sharp, of course, because A sharp is inside the thing, and the dual of something smaller is always something bigger than the thing,
Alright, okay.
the original thing.
So now, what are you saying when you say what is? I understand that there's a notion of order, so I understand there's an interval. Now, what were you saying here?
Where?
0 UA is included in A plus now. What are you saying here? Is it a fact? Is it a fact?
So here, let's put a subscript on here that says A star plus. We're using the canonical order on A star plus that's induced by knowing A to define this interval.
Okay, but
And that canonical order just says that probabilities between 0 and 1.
no, but what is the role of this interval now that it is defined? How do you use it? Like,
I don't know, I might not. It's just telling you what are legal measurements. What are legal measurement outcomes.
So the
Convex
other guys are not measurements. Like the other X which are not here are not measurements.
They're not legal measurement outcomes because their probabilities would not always be between 0 and 1.
So being decomposable as a sum up there and belonging to that interval is the same thing?
Well, decomposable, you don't have to decompose them. They just, everything here is in the interval, and that's how I define them. That's how I define them. Yeah, it is. I mean, if they're positive.
So if an effect is to belong to a measurement according to the definition above, it's got to belong to that interval. And conversely, perhaps, every such effect can be computed into a measurement.
Yeah.
Okay, all right.
Okay. So, right, so I mean in quantum mechanics, right, this dual cone is isomorphic to the primal cone, right? It's also the positive semi-different operators. And evaluation of functionals is just a trace inner product. Maybe that helps, I don't know. All right, so this is just sort of setting up for formalism. I don't know, do people need more examples? Let me just draw a picture of the dual cone. Maybe that'll help a little bit. So, let's say you have some Lorentz cone like this. The dual cone will just sort of be something. It might be bigger or it might be smaller. It depends on the opening angle of the initial cone. But, here's this. Well, so this should be bigger. Here's some extremal point in the initial cone. If this thing is 90 degrees, that's where you stop. You can't go any further without getting negative. Or this thing is 90 degrees, you have to stop. And so you get this, in this case, it's a wider cone. I should point out that this Lorentz cone and also the quantum cone have this nice property that they are self-dual. So what does that mean? That means that if you, so you can always represent the evaluation of linear functional on something here by just choosing an isomorphism between the dual vector space as a vector space and the primal space. And then evaluation of functionals looks like an inner product, it induces an inner product. So if you can do that, if you can pick your isomorphism between the dual and the primal in such a way that A is actually literally equal to A star, then we call the cone self-dual. And that, it's important to note, is a weaker condition than saying the cone is isomorphic to its dual. An example of that is to take a cone with a square base, which is closely related to these PR boxes that were discussed in the last lecture. It's sort of the state of one box, the state space for one box, where you have two measurements you can make, and each measurement can have two outcomes. So here's the base, omega's a square. If you look at the dual cone of this, okay, forgetting about the opening angle, which I made too small, it's going to look something like that. So it's also a square. So the things are isomorphic. These omegas are affinely isomorphic. But it's been rotated by pi over 2. And there's no way to mess about with the inner product and get it not to be rotated by pi over 2. So this thing is not self-dual, but it's isomorphic to its dual.
I think you must have said it's a stronger condition than the...
What is stronger?
The self-dual...
Yes, I did. It is stronger.
And being isomorphic to it.
Yeah, the weaker condition is being isomorphic to it.
Yeah.
Okay. So, what's the right notion, let's say, of dynamics for this system? Well, now let's say we have a system A and B, and so that our dynamics might actually change the nature of system A into a system of type B. So, if phi of A plus is inside B plus, so it takes states to states. That's a reasonable notion of dynamics. For it to truly be operationally reasonable, will require something like U of phi of omega should be less than, so this is U and A, of course. No, it's U and B. Less than or equal to UA of omega. So it's like saying it's norm decreasing. It'll never take a normalized state to a supernormalized state, although it might take one to a subnormalized state. So you might get a state for which probabilities don't add up to 1, but it's always going to be less than 1 if you apply one of these maps. And in fact, it's kind of nice because you can take this thing, UB of phi of omega, and this is the probability of process phi. You can interpret it that way. So if any of you are quantum information theorists, you know about completely positive maps, and typically we allow trace non-increasing positive maps to be our operationally legitimate things, and if the trace is decreased, the trace of the resulting thing is interpreted as the probability that that particular map happened. And of course you can extend it to some, add some other map such that they add up to a trace preserving map, and that represents sort of an operation where you'll always get some outcome. Yes?
So if A plus here is some conic density matrices and B plus is some conic density matrices,
Yeah.
then that notion of dynamics would correspond to a positive map.
Yeah.
What we really want is a completely positive map.
Yeah. So we'll get to that.
Oh, okay.
I'll let me just tell you a little bit about that. So that's right. In quantum mechanics, this will give you all positive maps, and not all of those are legal quantum maps because they don't tensor right. If you have an entangled state and you apply an arbitrary positive map, tensor, let's say, the identity, or in fact, tensor some other map to that state, you're not guaranteed to get a state in our choice of tensor product for quantum mechanics. So you can fix that up in one of two ways, right? You could say, oh, let's cut down the maps, or you could say, let's increase the states. And if you increase the states, you won't get quantum mechanics. So in particular, quantum mechanics is self-dual. If you say, oh, I'm actually going to allow all states that I can get to from states on A via applying a product map, I'll get out of, well, let me not try to improvise that, but yeah, you could, there are sort of two ways you can think of dealing with this. Quantum mechanics is one way of doing it, but the nice thing about doing this in a category type framework is going to be that it generalizes the notion of completely positive in the right way. So just to say that the thing is a monoidal category is going to say that the maps have to tensor okay, and your tensor has got to be compatible with that. And you'll still have the ability to make some trade-offs as to, do I throw in more morphisms, or do I shrink the, do I increase the tensor product, do I shrink the morphisms? But so you might want to call some notion of a maximal monoidal convex theory, one where You've thrown in all the morphisms you can throw in. So there isn't any way of adding stuff and still being consistent. So quantum mechanics has that property. That, you know, the tensor product is just compatible with the maps you allow, the completely constant maps. Okay, so yeah, so let me just tell you a teeny bit about category theoretic version of this. It's fairly simple. You know, the unit object is going to be R plus, and you know, omega is going to be 1. Its dual is also going to be R plus, and you know, 1. Okay. Let me just say something important about this star that I've been throwing around. It's not the same thing as the star that Jamie? Yeah, Jamie was using, and people have been using all over the place. I mean, it will be in nice cases, like quantum mechanics, and somewhat more general cases. But this dual cone is not an object in the category. So if we have a category of, you know, concrete ordered linear spaces where the morphisms are some cones of positive maps between them, so it's enriched over ordered linear spaces, if we like to use jargon, then if we've got that, yeah, this dual cone is not actually going to be one of these concrete state spaces. It's going to be in probably the opposite category. It's going to be some other thing. But you don't, in general, have a measurement space that is isomorphic to each state space. Right? So if you do have that for some particular thing, it's probably going to be something like having a dual in the sense that Jamie and other people have been talking about. And it's a nice axiom to think about. And it helps you do information processing protocols, as we'll see. But yeah, U star is taking you out of the category, actually. In this, or rather, A star is taking you out, maybe taking you out of this category. So the sort of thing this category is it's a monoidal category. Tensor unit is this. And we're going to say it's enriched over ordered linear spaces. So the Hom sets, or the sets of morphisms, are cones. And so if we go from I to some system A, you know, these morphisms, there's a whole mess of them, in fact, there's cone worth, are states, right? And so, you know, if you choose something less than 1 in there, you're like preparing an unnormalized state. And then you've got all these morphisms, you know, back to the tensor unit, and those are like effects. Okay, and so we didn't actually say that we have to, yeah, we didn't say, well, this is some cone, this has got to be the dual cone. Okay, so this cone is like Hom IA, and that is the state, and this is like Hom AI, and that is the effects. Okay, so this is no longer a concrete category. It's a slightly different formulation than when you say the objects are positive maps, although I think there's some way that you switch between them. And I won't attempt to say anything about it here. Right, so that's a category-like picture of things. And you know, so for some problems, it's nice to think about categories. For other problems, you're really just dealing with some small object within something. It may have some composite structure, but you don't necessarily care about being able to freely tensor things up. Okay, so about our tensors. We initially defined a tensor product to be, so let's define the minimal tensor product. So now we have A and B. A tensor min B is just convex hull. Okay. So A tensor min B, if we're going to be really pedantic, let's say plus, right? I apologize if I start leaving pluses off and you think, oh, is it a vector space or a cone? Don't worry, it's what you think it should be. So A tensor min B, the unnormalized state space here is just the, so now we'll say the positive pole of alpha tensor beta, where, you know, this is obviously an A plus and this is an E plus. So it's the generalization of the quantum definition of an unentangled state, right? Take pure product states, take their convex hull, that's the unentangled quantum, or sometimes they're called separable, right? Which is just asking for trouble, but when you get into serious math. But, I haven't gotten into math that serious yet. So, right, so this is like the unentangled states. Okay, what's the other thing? Well, it's A tensor max B plus is, okay, it's equal to A tensor min B star star all star. What in the world did I do that for? It's extremely intuitive, right? It's just as intuitive as this. This is saying, take the convex hull of product measurement outcomes, right? Only allow, only consider local measurements. And, the convex hull of them is a little trickier. You actually can't necessarily do it locally with classical communication, but it's mathematically natural. And require, and that's what this dual is doing, of course, because we want a cone of states, not of measurement outcomes, but require that your states be positive on all product measurement outcomes, right? So this lies inside there. If A and B are quantum mechanical systems, the quantum tensor product is strictly between these two things. And this, as I said, is the unentangled quantum states. This, well, if you think about the Choi-Jamelkowski isomorphism, if you know that stuff, this cone is basically isomorphic to the cone of positive maps from one system to the other. And so we know you've got things like a state corresponding to the state corresponding to the transpose map. That's not going to be positive on all entangled quantum states. It will be positive on all product outcomes. That's kind of why it's a good entanglement witness. Yes?
It seems to me this is almost certainly going to behave like a sort of tensor and power and linear logic. One is included in the other.
Yeah.
The formula is familiar.
It might. So we've been talking a lot with, Bob and Dushko. So
Yeah, so this is exactly the construction of part and tensor in a compact
I
category.
wanted to wait till the end of the talk to make this remark, but this category that you're describing here was described by Girard in a paper in 2002, and we called them quantum coherence spaces. We formulated them a little bit differently, but I reformulated it in a paper in 2004, more or less in exactly the same way that you're formulating it. So it either is well known or should be well known to all the logic crowd.
Okay. Well, I mean, just because there was one paper in reformulation doesn't mean it's going to be well known. But it's sort of natural
for those of us who actually were at the talk.
So, I mean, you can actually formulate this thing as a... So this omega induces what's called a base norm, in fact, on this space. And if you're a quantum information theorist and you say, what the heck is this? Well, the base norm distance is the trace distance that you use in... It's a very nice thing for quantum information processing. It has an operational interpretation in terms of distinguishability. Maximal distinguishability or something. So it's very nice, and you just take omega and minus omega and their convex hull, and that's the unit ball, and that's your base norm. And so you can actually think of this thing in terms of Banach space morphisms, and I would say I don't like to make the contractive, meaning non-expansive maps, the morphisms. I like to just leave all the morphisms around and have this category be traced with this UA, and that I don't know, I think that makes the mathematics nicer, and when you need to figure out whether the thing is legit or not, you use your tricks. But that's not entirely worked out. Okay, so tell me afterwards, and I will write down the references because I want to take a look. I think I did run into some of these ideas in some of your papers about taking contracted maps as morphisms.
Howard?
Yeah.
So using this Choi-Jamelkowski isomorphism, is it possible to single out a tensor product that's analogous to the quantum one by, say, using the completely positive maps in one of these theories?
I mean, we've tried to do that, but the answer is basically no, right? So, I mean, you don't have these things aren't in general self-dual, right? So the Choi-Jamelkowski isomorphism is going to be between states in a tensor product and maps from A star to B. So those aren't even at first in your category. They're not morphisms in the category. They're morphisms sort of from the opposite category to the category. So there may be some big thing in which you can look at these things.
But a self-dual theory, then maybe.
Yeah, in a self-dual, that's a question I've been asking a lot. Is let's say we've got two self-dual cones. Is there a canonical self-dual tensor product of these cones? If somebody wants to work on that, I think that would be a great thing to think about this workshop. Okay. So I haven't gotten as far as I want, but this is probably important to get the basics going right. Just a little point. If we had these sharps, right, these smaller cones, the right definition operationally might well be to take A sharp tensor min B sharp, for example, yeah, and then the ordered linear space dual, and that's going to be bigger than this, right? Because we said the A sharps were smaller. So the right definition of A tensor max B plus, when we cut down these cones, don't allow all the measurements, could be something bigger. And that kind of stuff is going to get taken care of when you do this in a category theoretic way, because you cut down the cone by having less morphisms to the unit. And so, you know, the category theoretic version of these conditions should work fine, let's say. Okay, so but that's not something I'm totally sure about. I just know that there should be a consistent way of making a bigger maximal tensor product when you do this right, which means in categories. Although, okay. So I think going through the formalism was probably the most valuable thing to do. I think I gave you the rough idea about broadcasting, the classical sets of states, so I'm not going to go over that in detail. Broadcasting and cloning. Direct sums of cones, okay. So basically, you know, if we, any cone C decomposes as a finite direct sum, infinite images of cones Ci, and these are like super selection sectors, and the point is that all the extremal rays of the cone lie in one of the Ci. So there's only mixing between the Ci's. There's nothing else interesting going on. Which summand you're in is classical information, and it's immutably classical information. There's no way to get superpositions of them. So you can gather that kind of information about which summand without disturbance, sort of measurement disturbance thing. And that's the only kind of information you can gather without disturbance. So that's a theorem by, you know, John Barrett, Alex Wilson, and Matt Buford, which is, well, it's at least announced in one of John's papers, and we might write it up soon in combination with, we want to show that how it relates to crypto, right? So something like in any non-classical theory, you can do key distribution a la quantum. And I mean, John actually has worked that out. I don't know to what, anyway, so that should be to appear, the key distribution. So I don't know if any of you have heard of this program that Chris Fuchs and Gilles Brassard like to promote, which is sometimes called the Fuchs-Brassard conjecture. Oh, maybe the conjunction of, you know, allowing key distribution but not allowing bit commitment, that's enough to get us quantum mechanics. Okay, I don't think it's going to be, but you know, if you're interested in that program, that's one reason to be looking at crypto in these structures. So let's look a little bit more at crypto. Let me just say that so with Ben Toner and those who else? Yeah, Oscar Dalston. I guess he was a student at Imperial. Now he's at ETH doing postdoc. Matt and me, we showed that if your system is non-classical, but you always couple with this minimal tensor product, so you don't allow entanglement, then there is an exponentially secure bit commitment protocol. So what's bit commitment? Basically, it's a sort of formal model of a functionality where you have a absolutely secure lock box where Alice can stick the thing in the box, lock it, keep the key, give the box to Bob. There is no way Alice can open the box while Bob has control, and there is no way Bob can open the box while Bob has control. So Alice can't open it and mess with the bit. So she's committed. Bob can't open it, find out what the bit is. So the protocol's hiding. So it's binding, we say, on Bob, and it's binding on Alice, hiding to Bob. But then at some point there's this reveal phase where Alice gives Bob the key. She can now open it and find the bit, and she knows that it is the bit that was committed to. In classical crypto and distributed computation, it's a powerful primitive. You can reduce a lot of things you want to do to it. It's also not possible with information theoretic security in classical mechanics, or classical theory, classical probability theory, let's say. And it is not possible with information theoretic security in quantum mechanics. Basically because you can use entangled states to kind of mess with things, turn your 0 into your 1. You know, there's no way to commit to not being able to turn the 0 into 1, because if you keep something entangled with 0 versus 1, you can mess with it and switch.
So, when you say not possible, you mean not known to be possible?
No, known not to be possible. Modulo a few people.
But for cryptographic security, it could be possible.
What?
Cryptographic security, it might be possible, but not with information security. Is that right?
Yeah, so with computational security, it might be possible, and it probably is possible, massively, but not with information security. So our protocol is very simple. It, you know, it's just sort of a simple-minded generalization of one that Ben and Broussard introduced in BB84, when they introduced QKD. They said, oh, let us look at the block sphere, which I think you've heard about already. And now let's say we're going to use either 0 or 1, or you know, minus or plus. I don't know if I put these in the right spot. I don't care. And we have two different ensembles. We'll either send this or that with probability 1/2, or this or that with probability 1/2. And which bit you commit to, which bit Alice commits to, 0 or 1, is represented by which ensemble she draws from, right? And because the convex hull of this and this, and the convex hull of this and this are the same thing, the uniform density matrix, identity over 2, Bob is not going to be able to find out anything about which ensemble was used. But Alice has to keep the draw, the pure, you know, information about which pure state she drew, and then she tells Bob, to reveal, she tells Bob, oh, the bit was 1, and here's the state. You do a measurement in this basis and check that it actually was this state. Because if it was one of these, you're going to have probability 1/2 of getting that state. And you have probability 1/2 of being detected as a cheater. So it doesn't work in classical mechanics because you keep an EPR state. And we know by this so-called Houston-Joseph-Witters theorem that I mentioned before that with an EPR state, by Alice making a measurement, she can steer to any ensemble for Bob's marginal. So she can make it look like she used this, or she can make it look like she used that. She does the measurement, whatever outcome she gets, that represents a pure state. That she sends that pure state to Bob. So you know, Myers and independently, I guess, Low and Chow showed this in '96, that these entangled attacks work for, you know, not just for this protocol, but any protocol, any computed bit protocol. So our theorem is just exploiting the fact that in any non-classical state space, for instance the square, you know, there are states, like this middle state, that have a non-unique decomposition into pure states. That is an alternative definition of what it means to be classical, in fact. If you want to define simplex, just say it has a unique, you know, non-unique decomposability. You know, I can recall people saying, oh, non-unique decomposability, peculiarly quantum mechanical thing. Well, it's not peculiarly quantum mechanical, it's peculiarly non-classical. So here's like the simplest non-classical thing you can think of, and here's something that has non-unique decomposability. And the point is just, all right, if you're in something like RD, you need something like D+1 of these states. You divide them into two different ensembles for a given state, mixed state. And we have a theorem that shows you can always find one. So you need this bound on the dimension is important. The states have to be exposed, right? These pure states have to be exposed. So there's some functional that has probability 1 on this state, and any other state that has probability strictly less than 1. But it's always possible to find, you know, a thing that's non-uniquely decomposable into D+1 exposed states in an arbitrary. So even if you have non-exposed states, and I won't, I'll just tell you, if you have like a stadium billiard, that point's not going to be exposed, and this point won't, right? Because whenever you tilt the thing around to try to pick it out, you suddenly pick up this whole line. That's straight. Thing's not smooth enough. But it doesn't matter because you can always find this ensemble with the exposed states, encode your bit into which ensemble you use, do this. Alice does a whole bunch of draws, n draws. She sends the state over, and then when it's time to reveal, she says which ensemble she used and which state each draw is supposed to be. And because there's no entanglement, you can't run this Low-Chow thing. against it. And because these states are all exposed, whatever other state in the protocol you might have sent in an attempt to cheat, you can show that there's going to be always a probability of detecting. So what Alice does is when she's told which state it's supposed to be, she knows it's exposed, she does the measurement that actually has an outcome that exposes it, and that thing should have probability 1 if the guy didn't cheat, or if Alice didn't cheat. And so she does this on every state in this string of n states, making the measurement Alice claims should have probability 1 for it, and if she ever doesn't get that measurement outcome, she aborts and accuses Alice of cheating. Well, it always will have probability 1 for an honest Alice, so the protocol's sound and it works. But you have this gap here, and basically, if it's less than 1, you repeat the thing a whole bunch of times, the probability of detecting cheating goes, the probability of successfully fooling Bob goes down exponentially. So you've got exponential security. And I think I'll probably stop there and invite discussion, although it might be nice to talk a bit about teleportation and about what kind of states allow steering of marginal. So basically, if you have an entangled state and you turn the state into a map by the typical way of turning states into maps, and that map is a isomorphism, at least in the case where both systems are identical, then you actually can steer. And that's also closely related to what you need for teleportation, which is also closely related to these cups and taps. But I think I'll stop. Yeah, Peter.
Sorry, not too much, but I have a question and also some comments. First, the question. So the information theoretic security of this last scheme also depends on the coding, right? Because Bob could just give any number of probabilities that measures all kinds of possible directions. So does not coding also hold for these abstract components?
Yes. So that I talked about that in the introduction, and I didn't come back to it. But yeah, if the state space, the only things that can be cloned are, a set of states that's clonable has to be the vertices of a simplex of perfectly distinguishable states. And so, there must be, there are states that are not in the convex hull of such a thing if you have a non-classical theory. And we need those states to do this protocol because we want non-unique decomposability, and that's telling you that it's not in the convex hull of the simplex. So yeah, it's closely related. Yeah, Alicia.
Was this protocol, is it unconditionally secure or cheat sensitive?
Unconditionally secure. So it's perfectly hiding, perfectly sound, and exponentially binding, which means that if you take the probability with which, so Alice does something. Now we add up the probability with which she succeeds in revealing 0, and the probability with which she can succeed in revealing 1, based on her later choices, right? So these things don't have to add up to 1. They could add up to 2 if the thing was totally rotten, like they would add up to 2 in classical. The sum of those probabilities is can be gotten within epsilon of 1, where epsilon is proportional to 2 to the minus n, where n is the number of systems. So that's what exponentially secure means here.
I just have some more comments. So first of all, I want to, the first half of the talk was about the clones and so on. I want to strongly endorse this. I think all of us who do logic and try to do semantics and describe quantum protocols and so on, we should all be looking at categories of clones, and that's the right setting to do all the things that we want to do. For example, how you said that a clone can be decomposed into essentially a byproduct of undecomposable clones. I think, and that's classical information to tell which component you're in. I think that is the right way to do, for example, to talk about classical data types. The other remark is that this kind of category is, I don't think you said it, but it's a star autonomous category with also with products and tensor particles.
So,
It's not a compact closed category because you have the two different tensors, right? The max and the min, and in linear logic they're called tensor and par, respectively. One corresponds to and the other to or.
yeah,
But,
so this is something that, with the star autonomy, yeah, it might be star autonomous if you have these two tensors, but I'm a little worried because there are some results I didn't tell you about that might cause trouble with that for this particular. So what I'm thinking about for these categories that correspond to a particular theory is you just pick some tensor product that's in between here, and then you impose the coherence condition. If you're dealing with categories, it should be, say it's monoidal, not necessarily symmetric. What worries me is this. So I might get it wrong, but okay. So just consider these two things. A tensor min, A tensor max, A tensor min A, and I think A tensor max, A min, right, max. So one of these, I can't remember which at the moment, has serious problems. So what are the problems? Yeah, so the point is, basically, you got to worry that you might be able to teleport. You have these super entangled states, right, that go along the max direction. But then you also have these entangled measurement outcomes in the min direction. I mean, it's not utterly clear that you have them because you need to look and find out what the subsystem of two things here is. But the problem is that sometimes you think this thing is legal, but then you could teleport a hyper entangled state here over to where it's not supposed to be. And so these things are what we call non-regular, right? So the conditional state space, the space of states you can get conditional on measurement outcomes, is not equal to the marginal state space. That's one way of talking about it. And so the thing is not a regular composite. You can't necessarily look at every coarse graining of the thing as being some nice tensor product with any choice of a tensor product in our sense. So that's what we impose that when we talk about teleportation. We impose regularity so we're not getting in trouble. Yeah.
The food panels, yeah.
So maybe Peter and I continue, and anyone who wants food should grab it.
Well, it does fall on
Okay.
especially when you have